And speaking about computers, we'll hear first from Scott Hughes, who was just telling me that he was given a very important leadership role at MIT.
Division head for astrophysics.
Division head.
Yes.
That means that people trust his judgment well beyond science. We trust his work on general relativity. So, who is introducing? Okay, go ahead.
All right. So we're very happy to have Scott Hughes today for the first talk. So Scott is a theoretical astrophysicist. He's a professor at the Department of Physics and the Kaplan Institute for Astrophysics and Space Science at MIT. He's also taught the first class I took on general relativity. Today he's going to be talking about the extreme mass ratio.
All right,
problem.
thank you.
Yeah.
Thank you. I was just rejoined Avi. I think it may also mean this. No one else was smart enough to say no. I said everyone else said no before they got to me. So that's what these things generally go. So I'm going to be talking today, sort of in the. I could talk about this for quite a long time, but what I'm going to spend is sort of an overview of work which has been my primary research focus for the past couple of years, which is exploiting the large mass ratio limit of the two-body problem in general relativity. I'm going to talk a bit, there's a particular aspect of this thing which has strong astrophysical motivations, but in my last couple slides, I want to motivate the fact that this is, there's some evidence just emerging now that this could have surprisingly important broader uses beyond this large mass ratio limit. So whenever I'm motivating this subject, I like to point out that if Einstein had never come along, this would be my whole talk. Okay? If you want to describe the two-body problem, and all we have is Newtonian gravity, you get two masses, you can reparameterize them a little bit, you have an M1 and M2, and then you have two parameters, an energy and an angular momentum, got some initial conditions, but you have a couple of quantities you define, a quadrature to do, boom, that's the entire two-body problem, Newtonian gravity. So if Einstein hadn't come along, this is where the talk would end, and I'd say, are there any questions? Of course, Einstein did come along. So the equivalent problem, if I want to formulate this in general relativity, is very different. What I would need to do first is split space-time into space and time. So here's two spatial slices. There's other ways you can do it, but here's the way it's often done. You have two spatial slices at different moments in time, and I put coordinates into these things that I'm going to use to describe some of the fields that I'm going to work with. I'm going to pick a geometry on each spatial slice, or rather I should say on an initial spatial slice. It shouldn't say on each, that's a typo. One of them basically being the metric in that slice, the other being essentially the time derivative of the metric in that slice. I will require that these fields obey some constraint equations that relate their properties to the density of matter and the flow of momentum in this space-time. Then I allow it to evolve. Ta-da! All of general relativity in four equations. But if you look at this, where are the bodies? Okay, and I'd like to see my aphorism for this is that general relativity is not really a theory of bodies, it's a theory of spacetimes. It doesn't have a two-body problem, it has a one spacetime problem. Now, clearly two-body systems exist, and so kind of the challenge is to connect that description of gravity to this reality. And so this is clear when you've got baryonic bodies. Okay, if I've got two bodies full of baryons, there are two bodies that are made out of matter, you can clearly define where one body ends and where another body begins. Okay, and that makes sense. I can't really do that if my bodies are black holes very carefully. I need to know where the event horizon is, I got to make some decisions about things, there's a lot more arbitrariness. I can also do this if I have widely separated bodies that allow me to define a slow motion limit. That lets me develop the equation of motion that describes, say, body 1 moving under the influence of body 2. And the Cauchy-Newtonian expansion of general relativity is based on this. It gives us a crank that recovers Newtonian gravity and then adds in some corrections to this. Okay, and you just have a big crank you turn. You can get some more corrections, and you can get a couple more if you want. This is from a paper that's now 13 years old. You can look at the update to it to get the next couple orders or check the algebra. Anyhow, there's the reference, knock yourselves out. The problem, the other limit that allows us to clearly define two bodies in here is when you have a large mass ratio. If that's the case, we can treat the large body as being some exact solution, such as the Kerr spacetime, and treat the small body as perturbing it. And so the kind of, at least conceptually, the problem to think about is I'm going to take my spacetime as having the form that's got an exact background that I understand. I'll take it to be a Kerr black hole, and then something is sort of pushing me away from it that's going to depend on the properties of the small body that is in this order there. This actually, this particular form, the way I've actually written it here, this is fine if it's a Schwarzschild black hole. Basically, it's because of the symmetries of the Kerr spacetime. It's a little bit nasty to try to do this with metric perturbations if it's a Kerr black hole. But if I can get technical for just a moment, the curvature equations do in fact separate. And so conceptually, what you can do is think of taking your Bianchi identity. What you should really do is act on it with another derivative to change the Bianchi identity into a wave equation. Expand your curvature around a Kerr background. Use the famous identities developed by Newman and Penrose many years ago to select useful components of the curvature. So you define a tetrad of an outgoing null direction, an incoming null direction, an outgoing null direction, and then mu and also its complex conjugate describes sort of the orthogonal directions to ingoing and outgoing at every location. And when you do this, you end up picking out two particularly important pieces of the curvature, one of which describes ingoing radiative perturbations, and the other describing outgoing radiative perturbations. And this was sort of first developed in a systematic way by Tucholsky in 1973, and explored by him and Bill Press in the early 70s. This gives us a complete description of how these two fields, the psi0 and the psi4, give us a complete description of the behavior of curvature perturbations to a Kerr black hole. That's going to be the engine that I use in a later part of the talk when I tell you about some of my results. So what is motivating this work? Astrophysically, this is motivated by well, many things motivate it, but the one that informs much of what I'm doing myself these days are trying to model, whoops, went backwards, went forward, my mistake, systems that we call the extreme mass ratio inspirals and also some intermediate mass ratio inspirals. So the EMRIs, the extreme mass ratio ones, these are astrophysical systems in which we think about multibody scattering happening down in the central parsec or so, central fraction of a parsec of a galactic nucleus, where you expect over the course of some time interval, and you can see, I can give you papers so you can map out what that is, you will occasionally get a 10 to 30 solar mass body put onto a strong field orbit of the massive black hole down there at the core. This thing will then, if it is tight enough, it will evolve solely due to gravitational wave emission, and it will have properties I'm going to show you in a little bit that allow us to really map out the space-time of these objects, of the bigger object as a small object via gravitational wave emission spirals through that strong field and generates all those gravitational waves. These events are very rare per galaxy, but they generate gravitational waves that are loud enough that the planned space detector, which is at last sort of in a more healthy state and is, sorry, I keep pitching the button by mistake, is likely to launch in the next decade and a half or so. Each one of these things can be sort of heard out to a redshift of on the order of, okay, it might be a half, might be 2, might be 3, depends a little bit on the properties, but definitely out to sort of nearby cosmological volumes. And when you fold that into the statistics of what we see in the cores of galaxies, we sort of expect up to hundreds of these events over the lifetime of the least emission. Okay, it could be as low as several tens. Some people think it could be as high as thousands, which actually causes other problems, but hundreds is probably a good ballpark number. Now, it's also the case, this is something that many of us has motivated much of our work for quite a bit of the last 2 or so decades. But lately, I've actually become interested in the implications of this for intermediate mass inspirals that may follow from high redshift galaxy mergers. So if we think about the kind of events that form the first galaxies we see around us, sort of, yeah?
Is large mass ratio the limit the same as extreme mass ratio, or?
I'm being somewhat imprecise with this language. When I say extreme, so this is like 10 to 30 solar masses in the small guy, and the big guy, millions or so. Okay, when I'm going to talk about, when I'm talking about the intermediates, and I'll get to your question in just a second, I'm thinking about, and I'll describe the astrophysics in just a second, several tens to 1 to several hundreds to 1. And when I say large mass ratio, I'm kind of being agnostic about which of these that I mean. I essentially just mean I want to deform away from the comparable mass ratio regime that numerical relativity has celebratedly done much of its work on. Okay, so I kind of want to encompass all of that, which is why I have a somewhat vaguer term in the title there. So for the intermediate mass ratio ones, when we think about the formation of the first galaxies, we're expecting that many of those first objects will have black holes at their cores, and it's really not known what the mass of those things may be. Okay, they might form from processes that leave behind 10,000 solar mass black holes, or they could be population 3 stars, and they could be 100 solar mass black holes or 50 solar mass black holes. But what is seen in some of the simulations that are studying the first assembly of these things is that at least the objects that are merging tend to have mass ratios that are more like 10s to 1 or 100s to 1. And if that is a decent proxy for what the black hole masses in there are as well, that sort of tells us that we could be getting very interesting events at high redshift where we have these large but not quite so extreme mass ratios
Well, it's not
associated
just
with
at high redshift, because at every redshift, most of the mergers that bring
Yeah.
dwarf galaxies into the middle of Milky Way
Good point.
galaxies
Good
are
point.
also 10 to 1.
That's right. Yeah, that's a good point. And one of the points, in fact, I'll just sort of give away a little bit of one of my points I want to make, is that when you're in mass ratios like this, it's very hard to do a model of this with a full numerical relativity code, because you need to resolve such a diverse range of length scales, and the simulation has to be able to follow it for tens of thousands of orbits. And so this is in a very uncomfortable regime for the full numerical relativity studies that have successfully modeled many binary black hole mergers. And I'm going to kind of argue that black hole perturbation theory gives us a good tool for modeling these. All right, so I'm going to focus. So how am I going to model these things? My 0th order model is I'm just going to begin with a bound Kerr geodesic. So here's a plot taken from an old paper of mine, which you sort of see that a typical orbit is going to be something that is eccentric, strong field, and it'll have an angular momentum that's misaligned from the black hole's spin. And what that does is it defines a torus in the region near the event horizon that in almost all cases it ergodically fills. And the reason it ergodically fills it is that the orbits of bodies in this thing have 3 independent timescales. They have 3 orbital frequencies associated with it, or 3 orbital periods. T sub r is associated with the radial motion. So this is the time it takes for it to go from periapsis to apoapsis and back. T sub theta is associated with the polar motion. That's the time for it to oscillate through its range of polar motion. And T sub phi is a time scale for this thing to wrap around in the axial sense. And what we see, so if I plot the inverse of those time scales for a particular example, at very large orbital separation, they have, of course, all 3 of them asymptote to Kepler's law. But as we move into the strong field, the 3 separate from one another and exhibit very different behaviors. Okay, it's almost like curvature of space-time acts kind of like Zeeman, like a magnetic field acts to split the hydrogen lines, and it's almost like a Zeeman splitting of Kepler's law.
Is there any chaos or no chaos in the GR?
Can we return to that question a little later? In this limit, none, but hold that thought. So I'm going to put a small body on this orbit. I'm going to use Tucholsky's framework to compute the perturbation that space-time arises from it. And the key thing I want to emphasize is that I can introduce this multipolar decomposition, this frequency decomposition, and then I have simple ordinary differential equations that govern the radial and the angular behavior of this. Once those are known, we can deduce how the small body is back reacting on the spacetime and how its orbit evolves. Okay, and this has turned into sort of an industry that many of us are now following to study these orbits. So the first approximation to this, what I'm going to do is average all of my various quantities over orbit timescales. Okay, so when I do that, at large R, the field psi 4 encodes the radiation. So once I have this particular Tucholsky field, this particular field calculated, that tells me what the gravitational waves look like far from the system. And from that, I can calculate how the quantities that govern the behavior of the orbits evolve with time. The other field encodes a tidal interaction between the orbit and the event horizon. Once I know that, I can get some analogous fields that describe the geometry of the event horizon. I'll describe a little bit more of that a little bit later. And likewise deduce how they influence the behavior of the orbits. So once I know them, I'm in good shape and I can calculate how the smaller body is driven to inspiral and eventually plunge into the larger black hole. So the way we actually do this is essentially, and this is the stage where many of us are at in the research right now, it basically boils down to just killing trees with Beowulf with compute clusters. Okay, we're just sort of running codes over and over and over again to generate giant fields of data. So here's an example of one of these fields of data. So what I'm doing is I have set up a set of orbits, so in this particular case, just so that I can make something two-dimensional, these are equatorial eccentric orbits of Schwarzschild black holes. And at various points in this space, I calculate how the orbit tends to evolve due to psi 0 and psi 4, due to these fields. And it defines how that orbit tends to move due to the back reaction of gravitational waves. And so what I essentially do then is I get these flow lines, and I flow along those lines, construct an inspiral. once I have constructed that inspiral, I know the amplitude and phase of the gravitational wave everywhere along there, and I can just integrate it up and put it together. So this particular case, as I said, I'm doing equatorial and eccentric orbits. Here's another two-dimensional example where the tail of each arrow is, this represents orbits that are of zero eccentricity, but they're inclined, and it sort of shows the way they tend to evolve in orbital radius, orbital inclination space. So at this point, we basically just need to generate a ton of this data and make some tools for studying the waveforms that result. So that's something that my group and I have been doing. And so here's an example. So this is actually for an inspiral. I should have said this is what the spin was. This is a Schwarzschild example. I start at relatively weak field, sort of 12.5 m, highly eccentric. And you get this structure like this initially. As the inspiral proceeds, the separation shrinks. All the orbital frequencies get higher. The binary circularizes, and you can see that by the reduction of contrast between the amplitude. This is what it looks like at periapsis when it's moving fastest. This is what it looks like at apoapsis when it's moving slowest. Similar thing happening over here. The reason for the two colors is that we've done this calculation two different ways. One using a code that we are tuning up to be faster. The other one is sort of more general purpose, but quite a bit slower. And so this is part of the work that's in preparation with a former postdoc of mine, where we're just demonstrating this new technique, the new data sets we put together. So I can take all of these things, stitch them together, and make an inspiral. And what we basically do then is you sit down and you make yourself a nice simulated gravitational wave inspiral. So this one, there's also accompanying audio, but I'm going to spare you that. But you can hear the gravitational waves in this if we plug this into the room. You can also just download this from the web. So
It
you want to hear
won't work.
You can hear it on the laptop. So let's entertain Avi. One thing I want to note, if you're watching this, you will occasionally see the motion appear to sort of freeze into a pattern. What's going on here is that occasionally during this inspiral, these three independent frequencies just momentarily pass close to a small integer ratio. When that happens, the orbit actually does not fill that torus. It traces out a Lissajous figure in that torus. And there's some implications of that I'm going to describe a little bit later. Okay, at this point it plunges. This was a movie that was made by a student of mine many, many years ago, and it used to be, I think this has been fixed, but I haven't updated it. When it hit the last frame, my laptop would reboot. So I just, I stopped it there. Hasn't happened in a while, I should really fix that. All right, so one of the things, that's how we make these models, okay? And so one of the things we're working on these days, and you know, the code that does this, by the way, there's a slightly reduced functionality version of this that has now been released to the public. If you Google the black hole perturbation toolkit, look for Gremlin. Gremlin is my package. It stands for Gravitational Radiation in the Extreme Mass Ratio Limit. But lim sounded stupid, so I changed the final M to an N. The version that handles generic orbits is not quite ready yet, because I have a few proprietary libraries that are still linked into it, but we're working on making that available sometime in 2020. So I want to talk a little bit about some of the interesting physics we see in this. Yes?
Was there anything surprising or unexpected when you looked, any qualitative surprising features when you just looked at those?
When I just looked at those vanilla things, not really. It was sort of cool to see, you know, as you move into the strong field, you know, there's features that sort of make sense, and it was just nice to see them come alive. So one thing is that when you make a waveform like this, I won't play the whole thing, play a little bit of this, but there's a lot of harmonics that contribute to this. And so one of the things that ends up being important is understanding how many harmonics you need to get to really effectively model this signal accurately. And one of the things, we just move ahead, you know, there's a real difference between the number of multiples I need to compute to get the fluxes right, and there's a lot fewer than I need once I have all those fluxes at a certain level to get I have everything done accurately. I don't need as many to model the waveform that comes from following all those fluxes, for example. So understanding that was really useful. When you move into the strong field, you know, there's sort of strong precession effects. Figuring out how well I need to follow the multiples to get that accurately turns out to be useful. But in terms of things that are sort of surprising and interesting, I'm going to move into a few things related to that right now. So in this adiabatic model, I described how I can sort of think of this as there's flux of gravitational waves going off to infinity. There's also a component which is basically gravitational waves going down the horizon. It looks like radiation has been absorbed by the black hole. These absorbed gravitational waves have a very counterintuitive effect in many cases. when you include them, you actually retard the rate at which the system inspirals. Now you can't quite see this here in the back of the room, but on the top I'm showing some inspirals where I include the horizon flux. This is for a particular set of mass ratios going into a very rapidly spinning black hole, 0.998 m, okay, sort of the Thorne limit. And, you know, the longest case I studied here, it took 637 days to spiral, and this one took 513, this one took 226. When I just sort of invoked, you know, by fiat, I just turned off that down horizon flux. What I found was that it spiraled in faster. Okay, so I actually lost energy more quickly when I turned off the down horizon flux. 637 went to 610 days. The down horizon flux actually retarded the inspiral by 4 weeks. And it continues all the way along there.
It's not clear to me what you mean by absorption, because the wavelength of the waves is much greater than the size of the horizon. So how can an object smaller than the wavelength absorb?
Okay, there's a wide spectrum being emitted by these things, though. And so, but hold that thought, because I think this is going to become clear in just a moment. You're not quite correct, because there is a wide spectrum that are being generated here, right? Because, you know, there's multiple harmonics that are playing a role.
Bigger than
That's not all, but most I would say, yes.
So by turn it off, you mean you just don't include the back reaction?
Exactly. Well, what I did was I include the flux, the fields that go off to infinity, and then just by fiat, I turn off those associated with the horizon, because I just want to quantify what do those down horizon fields do in the evolution of this system. Okay, and what I find when it's
what is this large numbers?
Oh, so these are, you'd have to, the details are in a paper that I'm going to give you the reference to in just a moment. These are the number of oscillations it makes associated with the phi motion and the number of oscillations associated with the theta motion during that inspiral. Okay, so it's basically the number of days is longer when I include this horizon flux, and the number of oscillations is greater. It's a way of quantifying how much longer it takes for this thing to spiral in when I include this horizon flux.
Scott, so this is basically due to superradiance, right?
Oh, you're giving me my talk. Indeed, if you choose a different spin, the effect essentially vanishes. Okay? And so this particular spin I chose, and this is where I feel like you really are giving away the talk. So this is the value at which, at the equatorial ISCO, the axial frequency exactly matches the rotation frequency of the horizon. And when you do that, the effect essentially vanishes. And if I were to go to still smaller spins, what you would find is that it switches sign, and then indeed the horizon ends up, including the down horizon flux, makes the inspiral go faster, as your intuition might suggest. Now, to answer all of these sort of points, I think there's a better way to think about this, which is that it's not so much radiation absorbed by the horizon, but it's a tidal coupling of the orbiting body to the event horizon. So this is based on work by Hawking and Hartle and Hartle from the early 1970s, showing that there's this duality between the fields that we describe as down horizon fields and the geometry, the embedding geometry of the horizon. And what we see is that, by doing this sort of analysis, in a couple papers I did with some students, and a follow-up that was actually done with Bob Penna, who used to be a student at Harvard a while ago. We calculate, let me play that movie again. What we're doing is calculating how the horizon is deformed when a small body orbits it. And we find that it bulges, just like a fluid body will bulge due to an applied tide. That bulge, depending on the relative angular speed of the orbit in the hole, that bulge exerts a torque on the orbit. Sometimes that torque will actually speed up the orbit, sometimes it will slow it down. And one of the points, this is related to some work I'm doing right now with some collaborators in Italy, is that this is very precise, this is very sensitive to the precise manner in which the horizon responds to an applied tide. It really depends on how that boundary condition behaves. And so, if there is some physics beyond vanilla GR that affects this down horizon field, it might show up here. Yeah?
Wasn't this Hartle-Hawking effect, wasn't this exactly the thing that was reinterpreted as the membrane paradigm?
The membrane paradigm was a tool that was used to help to understand that, indeed, yes.
So does this have some picture in the membrane paradigm of what you're...
Indeed, that's actually, so, Kip Thorne was my PhD supervisor, so I got to see that stuff. And it was essentially on reading some of those papers that gave me the idea of taking those tools, casting them in a form where I could apply it to the kind of calculations we're doing here, and make little animations like this. I'll also confess that one of the reasons we made these movies is that the graduate students involved in this wanted to go into the software industry, and he wanted to be able to showcase cool graphics in his job applications. So,
And is the body that's subject to this tidal force profile close enough where it actually starts becoming deformed as well?
So we're treating, in this, for now at least, we're treating the small body as essentially point-like. So in principle, if it were a star, absolutely, or a white dwarf even. I'm going to come to the matter of the structure of this thing in another slide or two. That's a good point. So the point I want to make with this is that we have this influence of the tidal coupling of this thing here, and I think there may be interesting physics of the nature of the event horizon that could show up in here, and this is something some colleagues and I are thinking about right now. It kind of gets to this point. So up till now, we've treated the small body as though it were point-like, which is wrong. Okay? It will have its own multipolar structure, and that will couple to the space-time curvature. It's going to have some size. It will sort of taste the curvature of the background. The leading effect of this will come from the small body's spin. And so the spin couples to the curvature, and it will precess as the body moves along its orbit. This precession these couplings will change the nature of the orbits in the inspiral. Among other things, a new timescale is introduced related to the precession. And the motion then gets pushed away from sort of a normal geodesic. You had asked me about chaos a moment ago. When this is included, if you linearize these equations in the small body spin, it remains integrable. But when you include the next order, you lose integrability, and it could become chaos. It could become chaotic, rather. So a typical inspiral, without the spin being included, as I move across sort of the orbital separation eccentricity plane, I follow tracks that sort of look like this. You can see it circularizing, and then deep in the strong field, it starts spiraling in so quickly, it stops circularizing, even actually grows up a little bit there. This is a cartoon. We haven't quite calculated this exactly yet, but we can see some of the effects. When we include these precession effects, we expect there to be additional oscillations on top of this. And one of the things we're working on right now is folding these into the models, understanding what's happening, and various effects that are related to this.
This last stage that you're showing here is already the transition into plunge?
Transition to plunge happens sort of in the last, it's not, no. So I would say no. I mean, in this, you're definitely well away from plunge. But perhaps this little bit here is transitioning to plunge, yeah. So everything I've done so far assumes this adiabatic approximation where I have orbit averaged everything that I might want to calculate. And we justify this by virtue of the fact that the terms that we are neglecting, they tend to be small and oscillatory. So here's a cartoon showing what this looks like. So the red might be my full first order back reaction terms. And the green, which you can barely see underneath of it, is what they look like when I orbit average them. And they track pretty nicely. So there's a little bit of an effect that I'm throwing away, but the average variance tracks this very, very well. This is true as long as my orbit truly fills that torus that describes the orbital geometry. When I'm in a case where, in particular, the theta and the r frequency pass through a small integer ratio, they will be close to it for on the order of a few dozen or a few hundred orbits. And when that happens, effects that normally average away start to accumulate in phase with one another, and my first order back reaction gets kicked. I've exaggerated the magnitude here for clarity, but you can see that you get sort of a big kick happening here. And what we sort of see is that in this case, the system will move from one adiabatic track to another. This is another example of some fairly subtle physics that will certainly happen in these large mass ratio systems. And a lot of people right now are sort of worrying about how important does this actually turn out to be? How do we actually model and look for something like this?
Well, would this get messed up if you have corrections which are order 1% to 10%? That's what you're thinking?
Oh yeah, you absolutely would. This would be sort of at each one of these moments, it's sort of percent level effects to the adiabatic model. And that is sufficient that a full adiabatic template would lose phase with it. And you would have some trouble. Certainly, there's some work showing that you can probably detect most of the systems, but you're going to get significant mismodeling when you do this. And some work that I've done with a student shows that actually at resonances like this, you will in fact encounter at least one for every event that Lisa measures. So this is something we definitely need to solve. And some recent work that some of us have done recently has shown that there's potentially another source of these resonances. So if I have a third body close by, and my understanding is that galactic centers don't just consist of a black hole and one other body. There might be a third or a fourth or a 12th body close by. Its tidal field can similarly resonate with the emery and lead to a very similar kind of effect. And so this was an analysis that was led by my colleague Beatrice Bonga, starting a faculty position in the Netherlands soon. Really, really nice stuff. So let me wrap up by asking the question, how far can we actually push this limit? We can do a tremendous number of these things, and one of the things that makes it attractive is that the equations of perturbation theory are a lot easier to solve than the full equation of GR. Okay, we can run codes for these things a lot more quickly. So, we've generally thought of this as just appropriate for M resources, but it's just a general limit of the two-body problem. There's some work that is going to appear on the archive in a few days from my colleagues at UMass Dartmouth and with a collaborator at Caltech, showing that with a proper kind of scaling, and I can talk about the scaling if you like a little bit afterwards, point particle, sort of large mass ratio models, which are this dashed line, line up stunningly well with a system that was computed in exact numerical relativity. So this is, you can sort of see here, as I said, dashed line is black hole perturbation theory. Blue line is numerical relativity. This is at a mass ratio of 8. Okay, we have traditionally always thought that we would need to have mass ratios of hundreds or thousands for these techniques to be valid. And it works stunningly well, very far beyond this. So this has made us sort of excited that perhaps these tools can be used more broadly than just the Lisa-Emery problem. Perhaps this is when useful when we start measuring events that have larger mass ratios with all the kind of gravitational wave instruments. So again, emphasizing that these tend to be much faster, so they may help tremendously with that. In this vein, I want to show just a little bit of some work that was done with some students and I recently. Yeah?
How do we understand that? Is it possible that the corrections start at the ratio squared? Or?
So what I think the way to say this is that the ratio squared corrections are smaller than anticipated. And so the first order models work stunningly well when the ratio is not as large as you might expect. This is an empirical result right now. Bear that in mind. Okay, I think more work needs to be done to explore that. So if this holds up, there's some work I've done with some students recently looking at black hole mode excitation. So if you strike a black hole, it rings like a bell. The distortions associated with that striking will fall away by quasi-normal ringing. The manner in which it rings depends on how that hole is struck. So here's a case where I have an inspiral that's perfectly equatorial, and you get sort of a simple, at the end of this thing, you get this traditional damped sinusoid, and we do a mode analysis, and you find it's mostly the L equals 2, M equals 2 mode, with a little bit of L equals 2, M equals 1. Do an inspiral where it's highly inclined, you get a much messier waveform. Bear in mind, this is just looking at it from a particular viewing angle. It'll look different from different angles. And we find it's sort of a more ecumenical mixture of modes, sort of a broad mixture from L equals 2 down to L equals 2, M equals 2 down to L equals 2, M equals minus 1. A little bit of L equals 2, M equals minus 2. What we found in doing a broad survey of these things is that the way these modes are excited turns out to depend in a very simple way on just two angles. One angle that characterizes the misalignment of the orbital angular momentum with the black hole spin, and another angle that basically characterizes the phase of the system at plunge. When we went in, so this is just one example of what the excitation amplitude looks like as a function of these two angles for a particular mode, for a particular black hole spin. A whole bunch of these figures we've generated showing that there's this very simple dependence on these two angles. What's particularly cool, and we're doing a little bit of work to follow up on this right now, is that this shape we can write down analytically in the Schwarzschild limit. And when we look at how it behaves for Kerr, the corrections are so small that the Schwarzschild formulas carry over almost without modification, 1 or 2% corrections. So the spin that we're looking at this is that if we can show that this holds up at less extreme mass ratios, this will give us a tool for learning about the orbital geometry using only the very late merger and ring down waveforms. This is very exciting to me because a lot of the information about spin orbit precession is encoded in the early inspiral binary waveforms. And you need thousands of cycles to really call that out. This suggests that there's sort of at least some residue of that orbital geometry that's imprinted in the last couple cycles, which when you're measuring high mass systems, that's all the detectors are getting. So time will tell, and so I've been talking with some people in the numerical relativity community about exploring this and seeing the extent to which this holds up. Early stuff, and I'm very excited about it. So I will wrap up there. So I hope I've convinced you that this turns out to be a surprisingly effective way to model two bodies in GR. And it looks like we can use it a lot more widely than the system we originally assumed it was only good for.
The final angle is the angle with respect to the tangent to the horizon?
That's right. Yeah, so if you imagine that you're let's say this is the black hole spin, and I define the mismatch angle between the orbit and the spin like so,
Right.
then this thing can plunge anywhere in a range from here.
Right.
And where it happens to lie in there is going to sort of be an accident of the phase. But at the very least, one of the things we show is that the dependence on that is clean, surprisingly so. All right. Yeah.
You mentioned that higher derivative corrections might be visible in the dynamics of the horizon.
Higher derivative correction?
Higher curvature. You
Oh no! What I think I was. Yeah. So what I was referring to there. Let me come back to this. Is this? Sorry. This idea that because. Sorry, that's my daughter. This idea that because there's sort of a strong imprint of the behavior of the physics of how the horizon interacts with the orbiting body is imprinted on the waveform. I'm kind of agnostic about what mechanism could modify that, but I'm just suggesting that there's a sufficiently strong signal that if there were some mechanism for that, this might be a way to go and look for this. Okay. I kind of want to be agnostic about what that actually is. Maybe it's a higher curvature theory. Maybe it's just there's some field that at a particular wavelength tends to interact differently than GR predicts vanilla standard. I'm not going to propose a particular hypothesis. I'm just going to say this is a good way to look for it.
Okay, but space-time is still weakly curved there?
Yeah. So and absolutely, space-time is still weakly curved there. And so if we were to place a bet, my bet is GR is going to hold up. But still, I like the idea of having a chance to look for it because that would be a fun bet to lose.
Yeah. So you looked at the case where the smaller body in your Emery has some spin.
Yeah.
And there are some, you can imagine some scenarios where your smaller body is not a single object but a tight binary. I'm curious if you can expand this framework to look at the inspiral of a tight binary into the central black hole.
I see no reason why you couldn't hear this. Yeah, so it's this stuff.
Mm-hmm.
So one of my students is actually finishing up a paper right now with Carl Rodriguez, which does something similar to what you're saying. They kind of look at the three-body, they're kind of doing relativistic three bodies equation of motion. So they developed a really nice systematic framework for describing that, which, not to speak ill of my colleagues, but corrects some errors that are in some papers by Cliff Will and a few others. And what they find is that in the limit where you sort of have a big black hole and a tight binary, it actually ends up being described by equations that look just like this, in fact. Okay, because and it kind of makes sense. It's almost like it's the sort of calculation you do in effective field theory. The background has a curvature that's very long. If the binary has a scale that's smaller than that curvature, the curvature doesn't know it's two bodies. It just thinks it's some kind of an object with an angular momentum attached to it. And so this ends up describing its dynamics.
Excellent.
Yeah.
In your movies, that there's the small particle comes in and then it sort of gets stuck in a close orbit for 3 or 4 revolutions, and then it goes back out.
Yeah.
What is the energy exchange, and why does it have that time scale?
So that is what you're seeing there. Let me show you 2 plots that help to illustrate that. So first of all, what you are seeing is just perihelion precession on crack. Okay, I mean that's really all it is. And so what you're basically seeing here is a competition between the timescale associated with the axial motion and the timescale associated with the radial motion. So when you get down close to the black hole, you're down deep in the throat. It's a very non-Newtonian potential. Plus, if it's rotating, there's frame dragging. So it actually tends to whirl around several times just due to the fact that you're close and you're feeling that frame dragging. And so you're just really seeing the fact that there's such a contrast between these 2 frequencies here. And so when you have, let me see if I can show a movie that illustrates this, I think, most cleanly. Yeah, so this is a good one for this because it sort of allows you to see this. And really, you're just seeing the fact that this is a case where, the time to go from periapsis to apoapsis is much longer than the time scale to complete 2 pi radians in the axial direction. Okay, and this is really nothing more than the perihelion precession of the sun, but taken far to a far extreme. I should probably look at next speaker stuff.
You said that there might be a problem if it turns out that there are thousands memories during Lisa's lifetime.
Yeah.
What's the problem there? Is it interference?
Yeah, it's confusion. You get a little bit worried about confusion. So part of the work that we're doing right now to use, to model these waveforms, you can kind of see where it's going when I introduced this perturbative, this multipolar expansion of these fields. So psi 4, modulo a little bit of definition, is the gravitational waves far from the system. And so if you sum all these guys up, it's a mess, okay? But if you don't sum it up, each individual contribution is actually pretty smooth and well behaved. And so part of the trick that we're doing to model these things more carefully is rather than doing sort of, think of a single Emery waveform as being like 30 or 100 simpler waveforms superposed, okay? So that means every source is kind of like really 100 sources. Now imagine instead of having 100 sources, you have 4,000 sources, okay? So you've got 4,000 of these independently evolving sinusoids that you're looking for. You'll probably get most of them, but you're gonna start to run into confusion problems.
Okay, I guess we have to move to the next talk. Let's thank Scott again.
Grab my bag.
Okay, so our second speaker is Elena Giorgi. She's a postdoc at the Gravity Initiative at Princeton, and she's going to be speaking to us about stability of black holes and general relativity.
Is that the initiative that got the Nobel Prize?
Yeah, I mean, I guess people, yeah, I guess he's not part of the Gravity Initiative, but but he's probably emeritus, like, yeah, so, but
it's still the same group.
yeah, but yeah, it's the same.
And you're telling me you guys are very good friends and work together. Yeah.
Yes, right.
Anyway, Elena, take it away.
Thank you very much for the invitation. And yeah, the aim of my talk is to give an overview on the problem of stability of black holes in mathematical general relativity, because it's a very active field. So it's easy to miss some new results, and so I'm trying to give an overview of that. So I'm gonna start from the very beginning, which is what general relativity. What general relativity tells us is that space-time is a four-dimensional manifold with a Lorentzian metric that verifies the Einstein equation. So it's the Einstein tensor, the Ricci curvature, minus 1/2 Ricci scalar times the metric is equal to the stress energy tensor. So whatever mass you wanna, matter, energy you wanna consider in the universe is in the space-time is in the right-hand side of the equation. And this is the equation. And the second most important thing is that general relativity admits a well-posed initial value formulation. That is because of Choquet-Brouas theorem in the 50s, saying that if you give me an initial data for the Einstein equation, which is a three-dimensional Riemannian manifold, which verifies the constraint equations, then you can evolve in a unique way the Einstein equation. So this is the very basic, and I'm gonna throw there like a crazy idea about this. About this data, what would the evolution of this data be? Well, there is a conjecture, which is called the final state conjecture, which tells you that any generic asymptotically flat initial data of the Einstein vacuum equation, let's say, have then a future complete development, which can be described as a finite number of Kerr solutions which move away one from each other. So this is why I say it's a crazy idea, because of course I gave you an equation, I'm just telling you it's as a well-posed initial value formulation, but this tells you absolutely nothing about the behavior of the solution, tells you absolutely, you should have no idea of what the behavior of the solution will be. So this is a crazy idea, but of course it's motivated by some partially knowing facts, which is formation of black holes. So we know there exists a mechanism which creates black holes from gravitational collapse. So that's how you can at least say, okay, I can have black holes. There are some results on rigidity of black holes, the so-called no-hair theorem, which say that the only analytic solution which is explicit of the Einstein equation is a Kerr solution. But so this is something that can tell you, okay, if you form a black hole, it kind of has to be a Kerr solution. Yes.
This is stronger than cosmic censorship, isn't it?
Yes, it also, yes, it
you'd
it
have to prove
contains,
cosmic
yeah,
censorship
exactly, yes,
first.
yes. No, it's a crazy conjecture, yeah.
But are you ignoring charge?
Yeah, here I'm just saying for the vacuum, but you can do everything with charge. It would be a Kerr-Newman solution. Yes, you can do. Yeah, I'm just saying for simplicity vacuum, but you can put whatever reasonable matter field you can think of. So yeah, the rigidity gives you hope that say, okay, if you form a black hole, then it should be a Kerr solution. Okay, and then the third component is stability of black holes. If you perturb this initial data a little bit, then you should not have some crazy chaotic behavior. You should not have some crazy, let's see.
Good.
Okay, some crazy chaotic behavior, but you should still have a future development that behaves a little just like before. But these are absolutely open. All three open problems in mathematical general relativity. Some results are known, but we're far, far away from proving anything like the final state conjecture. This is. But I want to focus on the third one, stability of black holes, and tell you what's known about that. So then we have to go back to the Choquet-Boas theorem. So I told you we have an initial value formulation. So this means that by Choquet-Boas theorem, the Einstein equation in wave coordinates can be written as a strongly hyperbolic system. So it's a box of G is equal to some no linearity in G and first derivatives of G. And now, since for strong hyperbolic system we have local werposeness, then this we know we have local werposeness continuous dependence on the initial data. This is basically Choquet-Boas theorem. But these equations can have any source of behavior. So we have a local werposeness, but we have no idea what the global behavior would be. For example, if you take a solution of an equation of the form a box of psi equal to dt psi square, and you take as initial data t equals 0 and also first derivative equal to epsilon, then this will blow up in finite time for epsilon small. So this will means that an equation of this form, so you have a strong hyperbolic system, tells you absolutely nothing about the behavior. You have no idea that the space-time will blow up, and there will be just no. I'm scared of this. So even perturbation from the trivial initial data, so perturbation of epsilon, could give up to a blow-up solution. Okay, so this at this point you know nothing, but surprisingly this does not happen. Perturbation of the trivial data in the Einstein equation does not give rise to blow up, but actually small perturbation of the Minkowski space-time has a complete maximal development. This was a theorem by Christodoulou-Klein in the 1990s. And so why is this is surprisingly from a mathematical point of view. From a physical point of view, of course, one says, well, thank God, because otherwise we have to throw away the Einstein equation simply. But no, we don't have to, because from a mathematical point of view, what happens is that terms like dtg squared are not present on the right-hand side of the Einstein equation. So it's a very special equation. And this is what it's called the weak null condition. So this was Minkowski, so it's if you're not familiar, it's like 500 pages proof. Now, what if I want to understand the global behavior of non-trivial solutions, so of black holes? Okay, so that's what I want to do. Okay, then let me introduce, I will mostly talk about two specialized Einstein equation, which is the vacuum Einstein equation, which is equal to 0, and the electrovacuum Einstein equation, which is Einstein-Maxwell. So you couple the Ricci curvature is given in terms of a quadratic expression of a two form, which verifies itself the Maxwell equation. Yes?
Does that, the last slide imply that if you add generic...
this one?
Yeah, generic, like Lorentz invariant higher derivative terms to the action, that then you do expect this well-posedness?
Yes. Yeah, so you're talking, for example, Nesky theory, or like some modified, that's what you're talking about, right? Some modified theory of gravity. Then you have, for those modified theory of gravities, you don't even, for some of them, you don't even have a strong hyperbolic system to start with, so you don't even know if it has a local well-posedness. But even if you do, you absolutely have no idea what the global behavior would be. Yeah, so you will have to prove a theorem like this for the modified theory if you modify the action of the Einstein equation.
How do I reconcile that with the physical intuition that those terms should be irrelevant at long distances?
I mean, it depends on which theory you're talking about. Maybe they're not irrelevant in a crazy theory you come up. I mean, if you write down a crazy theory, it will not be irrelevant. I mean, that's my understanding. But I don't know much about modified theory of gravity, so I don't want to say. But they could not be. I mean, you have to prove something like that in order for it to be viable. I mean, to be like a viable theory. Okay, so these are the two equations I will concentrate, vacuum and electrovacuum spacetimes. And the examples of vacuum solution are Minkowski spacetime, Schwarzschild spacetime, Kerr spacetime. I assume most of you probably know these guys, but I will write them their metric. An example of electrovacuum solution, Reissner-Nordstrom and Kerr-Newman. So those are pretty much also the only solutions we know, like explicit solutions of, mostly of Einstein equation. Okay, so the conjecture about the global stability of Kerr or Kerr-Newman, since I'm talking about vacuum and electrovacuum, is that any small perturbation of initial data, where Kerr-Newman, let's say for the vacuum of a Kerr spacetime, which is a solution of the Einstein vacuum equation, has a globe future development with a complete future non-infinity, which behaves asymptotically like a Kerr solution. So the same exact theorem that Christodoulou-Kleinemann proved for Minkowski, we expect it to be true for Kerr. But it's not proved. This is not proved yet. And what I want to talk about is like some, what's known. Well, we know there are lots of results about classical mode analysis, which were done by the physicists in the 70s and 80s. What the mode stability analysis means is that one does not study general solutions, which is similar to what we saw earlier, of the Einstein, let's say the scalar wave equation, box psi equal to 0, but rather individual modes. So a mode will be a solution, let's say in Schwarzschild, a solution of this form. So if there is a radial, this doesn't work, okay. Radial, it's a radial component, so depending on R, these are spherical harmonics on the sphere. Let's say in Schwarzschild, in Kerr, it would be a bit more different. And then you have this frequency in omega. So these are some, it's an ansatz, you can say. So you're imposing this form, and the reason why this is a solution of this is because of the symmetries of Schwarzschild, because Schwarzschild is spherically symmetric. And so you can prove that if you plug this into the box, then you end up having an ODE for the radial part, which can be rewritten in these terms. So it's a second order derivative with a certain potential, which depends on the spherical harmonics. And then the mode stability consists in saying that there are no solutions of the form 3 with finite energy at time 0 and imaginary part of the frequency bigger than 0. Because if the imaginary part of omega is 0, then this will exponentially grow in time. This is what mode stability means. And mode stability of Schwarzschild, Reissner-Nordstrom, and Kerr is known. There are many works of people doing metric perturbations approach, so Reggie Wheeler, Vishwaswara, Zirilli, Moncrief, Newman-Penrose formalism, Barden-Press, Teokovsky, which was mentioned already, Chandrasekhar, Whiting. So these are all results were known. And back in the 80s was also known that there is a Chandrasekhar transformation that is now called Chandrasekhar transformation between these two approaches, metric perturbations and Newman-Penrose formalism. Now my point is that mode stability is not conclusive. Why? Because the classical mode analysis, as I said, can be used to show that some data with compact support, let's say, they grow at most exponential in time. So you can have a bound of this form, which is still completely consistent with the statement that this solution will blow up. So their limit as t goes to infinity will still be infinity, which is not what we want, even if you want to understand the actual stability of gravitational perturbation. And this is because statement of the level of individual modes do not imply statements of an infinite sum of them. That's basically what was referring to in the previous talk. So the mode analysis, of course, is a necessary condition. If you have a mode instability, then okay, you can leave it, but it's not enough, not even to prove boundedness of the solution of the linearized equations, for example. So that's what I want to talk about. I want to talk about how you can actually give some quantitative decay on that. And to do that, you need to go into the actual hyperbolic PDE. You can decompose in modes. You have to work with the box in its greatness. And you have to use something like the vector field method. So imagine you have an equation of the form of box. Let's say you have a potential equal to 0. Then you can define the stress energy tensor to this equation, which is a symmetric 2 tensor. And if you have a vector field, you contract these two tensor with the vector field. You have a 1 form. Then the divergence of this 1 form will be given in terms of the deformation tensor. So this is the Lie derivative of the metric with respect to x. And look at the derivative of the potential. So let's call this whatever divergence is E. And then the idea of the vector field method is to integrate over a causal domain of your black hole and apply divergence theorem. So if you apply divergence theorem to this identity, then you end up having here only boundary terms on the two space-like slices, and then you have a Bach term, so a space-time integral on the left-hand side. So what you want to do, you want to choose vector field so that the Bach space-time integral is positive definite that contains all derivatives, so that it will give you control on that. And you also want that the boundary term is positive definite and contains all derivative, which will be your energy. And so now so this is just what you want to do with the wave equation. Now I want to summarize what are the known results for Schwarzschild, Kerr, Reissner-Nordstrom, and Kerr-Newman. So the Schwarzschild metric, I've written this, so this is the round spherical symmetric metric. It has been proved to be linearly stable. So you see, these are all very recent work. So the first work by using curvature perturbation by the Reissner-Nordstrom in 2016, using metric perturbation by Jordan, he's here, Hung and Wong in 2017, and then using wave coordinates by Johnson and Hung in 2018, and also being non-linearly stable under a certain class of symmetry by Paineman-Scheftel last year. So this is what's known about Schwarzschild, and just a little bit of aside is that what does linear
Could
stability?
you go back one slide? All of these, yes, are all of these different, all of them separately required, none of them imply anything else? Curvature perturbation, metric perturbation?
No, you can derive, so they're all, if you had only one proof, one of these three, it would still imply everything else, yes. Okay. But they're just done in different ways. Okay. Yeah. So this is basically by Newman-Penrose formalism, this is by metric perturbation, so G goes to G plus delta G. And wave coordinates is just, to write everything in wave coordinates. So but they're all, one would be enough, I would say, so what does linear stability mean? If you take reach equals 0, and you can think of linearizing, so formally, sort of this would be like taking a Fresh derivative of the Ricci curvature with respect to the metric and evaluating at the Schwarzschild metric, this will be equal to 0, it's a linearization of your equation. But then, in doing linear stability means you want to study this linearization as opposed to the full Einstein equation. But then you have to observe two facts. That the Kerr metric, for example, if you do this in Schwarzschild, is still a solution, is a solution of Ricci equals 0. And every diffeomorphism, if G is a solution of Ricci equals 0, every diffeomorphism will give you, if you take every diffeomorphism and you take a pullback of the metric, will also be a solution of Ricci equals 0. That's because Ricci is a tensor. That's the definition of being a tensor. So this means that you have two instability in this process of linearizing, because no matter how well you want to study this equation, there's going to be a moment where you will have to change the parameters of the mass and the angular momentum, and there's going to be a moment where you have to choose the gauge. So this will be two four sources of instability. So just to give you an idea, I'll write you what's the theorem of the Fermat-Solzhenitsyn, and they say that all solutions to the linearized Einstein equation are Schwarzschild, remain uniformly bounded on the exterior, and they decay to a linearized Kerr solution after adding a pure gauge solution. So that's the best you can do. You can't eliminate Kerr. You have to accept the fact that if you're Schwarzschild and you perturb it, you can start rotating. So you can become a slowly rotating Kerr, and then you have to choose a gauge to actually prove stability or convergence. Okay, so this is the theorem. Now I'm going to give you an overview of how this was proved. So this was already mentioned before by the Tokowski equation. So there is this curvature component, corresponding to the psi 0 and psi 4 in Newman-Penrose. Penrose formalism, I'll call it alpha, because for me it's a two tensor. Those are gauge invariant components that they verify a decoupled wave equation of this form. So this is the Tokowski equation. So let's look at it. So this is a box of the Schwarzschild, plus, so now these are first order terms. So the ingoing and outgoing null direction with some coefficient, C1 and C2, and then there is a potential. Now, the good thing about this equation is that it's decoupled by everything else. The bad thing about this equation is the presence of these two terms. Because as I showed you before, the way you analyze the equation box and potential, they do not admit any first order term. You can know this because this equation does not come from a Lagrangian. So the way people analyze this, just as was mentioned in the previous talk, is by decomposing in modes. And then you can do mode stability. But as I said, most of it is not conclusive to actually prove boundedness of this equation. So what do you do here? Well, what DHR did was they realized that there is a physical space version of the Chandrasekhar transformation, which transformed this Tchaikovsky equation into a well-behaved one. Now, this transformation is not a trivial one. It consists in taking two derivatives in the ingoing direction of alpha. So let's say Q is two derivatives of alpha. So what I'm saying is that you take this equation that is not well behaved and you take two derivatives. It sounds crazy. It sounds like a very bad idea, because if you take two derivatives, you end up with all sorts of mixed terms. Well, there is a reason underlying it, but what happens is that most of the terms cancel out, and you end up having an equation of this form, which has a Reggie-Wheeler potential. That's exactly the same relation that in a fixed frequency space was found out by the physicist at the level of curvature perturbation and metric perturbations. So it's there in physical space. You don't need to decompose in frequency. This is in physical space. Now you have an equation box plus potential. I told you before, you can apply the vector field method and get decay for this Q. And now you can use the definition of Q to basically integrate twice this equation and get decay for alpha. And then once you get decay for alpha, you can get decay for almost everything else. Why almost? Because alpha is defined as the wide curvature contracted, here's a typo, this should be E4, contracted into the LL direction. So this is a two tensor, so it's supporting L greater equal than 2 spherical harmonics. So this means that any decay you have about this will only give you information about the L greater than 2 spherical harmonics. So part of their theorem is to prove that the projection into 0 and 1 is only given by a Kerr solution or a pure gauge. And this is basically how the theorem goes. So now let's see what's known in Kerr. So this is the Kerr metric, its glory. And then this one, very recently, so this both work are on archive, this here a few months ago. So this has been proved to be linearly stable for very small a, by using Newman-Penrose formalism by Anderson, Beckeldal, Bluma, and by using harmonic gauge by Hafner, Hinz, and Bagi. And again, the fundamental step is to prove boundedness and decay for solution to the Tchaikovsky equation. So let's see what happens in Tchaikovsky. Again, we know the same equation, this was found by Tchaikovsky in the 70s. This is the equation of the couples in Kerr too. Now, there exists a Chandrasekhar transformation in Kerr also. You take two derivatives of this equation, and now you get the part that was like in Schwarzschild, the Schwarzschild was equal to 0. Now here you have in Kerr, something, so you see it all depends on A, so it will be 0 in Schwarzschild. But now you have a first order term, which sounds bad. This is like the bad, like for Tchaikovsky, so that could be a problem. But it comes with I dt, so it's the t derivative of Q. So these are all derivatives, are all terms in Q. And now these are lower order term, because Q is two derivative of alpha, and here you have alpha, one derivative of alpha, one derivative, and two derivatives of alpha. So this is a lower order terms in terms of differentiability. So these terms can be treated as transport equation. And this one, actually, what it turns out is that this has still good divergence properties, just like if you didn't have this, because the idea is that if you multiply this equation by dt q bar, so in this there is an I coming up because you actually have to complexify in Kerr, it becomes easier. So if you multiply by q bar, by dt q bar in doing the energy estimate, this part will basically cancel out when you take the real part. So for this reason, because you have this term of exactly this structure, this is good enough to actually obtain decay for Kerr. And now I want to talk about Reissner-Nordstrom, which is what I did. So the Reissner-Nordstrom metric, I proved it to be linearly stable using curvature perturbation in both cases for very small charge. This was something that I did last year in my PhD thesis, and is actually stable in the full sub-extrema range. I think this was out actually today on archive as solution to the Einstein-Maxwell equation. So I'm trying to say what happens in Reissner-Nordstrom. So what are the equations? Now again, alpha, that's the first start, right? You want to see what's the Tchaikovsky equation in alpha. Now, you know it's 0 in Schwarzschild, but in Reissner-Nordstrom it's not 0. It's actually given by the charge multiplied by a first derivative of another quantity, f, which I had to identify. And then this quantity, I computed the wave equation of this quantity, and it's another Tchaikovsky equation which is coupled back to alpha. So this is a system of coupled wave equations which are coupled, two wave equations which are coupled one with each other. And now there is a Chandrasekhar transformation for both of them. So it consists of taking two derivatives of the first and only one derivative of the second. One derivative because this comes from the electromagnetic tensor, so it's a spin 1 equation. And these are the system that I get. So if you define Q, so the red one is the transformed of alpha. Now you have a Reggie-Wheeler part, which will be equal to 0 in Schwarzschild. But now you have the right-hand side, which depends on the blue QF. And the second equation is a wave equation for QF with right-hand side that depends on the red Q. And now in case of small q, so the first part of in my thesis, what I did, I derived estimates for this system. But there is a problem here because alpha and f are both two tensors, so the same thing as before. They only give you information for L greater or equal than 2. But now we have electromagnetic radiation, so it's not in vacuum anymore, it's in Einstein-Maxwell. So we need to we expect to have some radiation in L equal 1. And electromagnetic radiation is supported in L equal 1. So we have to identify one tensor that transports electromagnetic radiation. And this is a combination of curvature and electromagnetic, so let's forget about the definition. It's something that I call B tilde. It's a gauge invariant quantity. I computed the equation for this, among many other equations for many other quantity I was considering, but this was an equation that looked awful with a messy right-hand side, but it turns out of desperation I computed the first derivative of this, and actually there is a Chandrasekhar transformation that will give you a box with a Fokker-Ellipser equation. That's something that came up with in the electromagnetic radiation analysis, in mode analysis, equal to the divergence of the QF that you had before. So actually, you have three equations. Okay, so there is the red, the blue, and the green quantities. And it turns out that there is a relation between these two, between these three quantities. So there is a relation, this is a kind of an angular derivative. So it means that one of the equation is redundant. Okay, because there is a relation, but they're not all redundant in the same way. So you see, these are box 2, and box 1. This is a one form, these are two tensors. So it means that the way I was doing the estimates at the beginning is that I was forgetting this one, and I was doing the estimates for this part. But in this way, I was forgetting the L equal 1 mode. So what I really don't want to do is to forget this one. I have to forget one of these two. So, and of course, I want to forget the first one, which is the ugliest one, it has a Laplacian on the right-hand side. So let's forget that. Now I have a CRQ, I have to use the relation between Q, QF, and P to substitute Q. Okay, I do. And then what it turns out is that these lower order terms exactly cancel out. This term will just go change the potential. And I end up with this system. And this is really the exact system. So you have an equation for a one form, equation for a two tensor, and here you have the divergence of this this two tensor, and here you have a d2 star, which is an angular derivative minus the divergence of this one form. So now this is a diagonalizable and symmetric system because these two operators are adjoint on the sphere. So the way you analyze this system is that, so this is your system. I define a stress energy tensor, which is a modification of I define stress energy tensor that is defined in terms of the full system, which is given by the stress energy tensor of the first plus the stress energy tensor of the second, minus a combination of this dot product of the right-hand side. Then in this way, the divergence, this stress energy tensor has good divergence properties, meaning if I contract with a vector field x, so let's say you will end up having the terms that you had before, plus something depending on the right-hand side. And now, if you use it for x equal t, d dt, it's a Killing vector field, so this will disappear. The t of the potential is 0, so you end up having these two terms. Now, if you integrate by parts in t, you can bring the t on this other term. Now you can commute t and the divergence. And now if you integrate again by parts, the divergence and the d2 star are adjoint operator. So this will give you exactly 0 in the energy estimate. So it means that you have an inequality of the boundary terms that I showed you earlier. So the boundary terms of the P are equal. So if you show that those are positive, they're definite, you have conservation of the energy. So this is boundedness of the energy. And then once you have boundedness of the energy, you can prove, you can also do Moravec estimates and so on and so forth. So this is what we did in Reissner-Nordstrom. So the Kerr-Newman metric now, just to finish, the Kerr-Newman metric is this, its glory again, it's just like Kerr, but you have both A square and Q square, so it's both, it reduces to Reissner-Nordstrom and Kerr. And I just want to read something that Chandrasekhar wrote in its book. which said that the methods that proved to be so successful in treating gravitational perturbations of the Kerr spacetime do not seem to be applicable for treating the coupled electromagnetic gravitational perturbation of Kerr-Newman, and the principal obstacle is in finding separated equations. And here he writes many equations, and I just want to highlight these last 3 lines. It says that all efforts to decouple or separate these equations were not successful. Numerous other alternatives manipulation were equally unsuccessful. So this very much triggers me that in Kerr-Newman pretty much nothing is known, so it's clearly what we should do next. And yeah, thank you.
Questions for the speaker?
Yes.
So can any of these, are mathematicians willing to use computers with numerical relativity to test stability?
Yeah. So
with
if
computers, is it possible?
you mean to I mean, yeah, I mean, I'm definitely willing to just, I mean, it's what numerical relativity does in a way.
Not by mathematicians, by physicists right now.
Yes.
So I'm saying,
right.
Can you use computers to prove your theorem?
I mean, if it's a theorem, then it's not enough, probably. I mean, for example, we use many people, especially when you go in Kerr or in Kerr-Newman, you have to use, like, for example, Mathematica to do the computations. But that's different than running a code, yeah. So if you run a code, I'm not sure you can say that you proved the theorem, because the theorem...
You play devil's advocate. I mean, you can imagine that there's some numerical viscosity that damped out an effect that might be present that could lead to an instability or something like that. That would be, you change your algorithm, you get a different result, right?
But more so than that too, the numerical experiments allow you to do experiments, and you can't prove it, just like you can't prove a physical theory correct by doing the experiment.
Yeah, you can prove a theorem by doing,
You can't prove
well, unless you explore all parameters.
which you can't do.
Yeah, but it's,
Economics.
Can you do something for Kerr-Newman which is perturbative in either the spin or the charge? I mean, start from Reissner-Nordstrom and turn on a little bit of spin and then do something.
So the problem with doing like perturbatively is that it basically changes completely the geometry. So for example, as I showed from Schwarzschild to Kerr, you see like this, the equation box plus the equation you had in Kerr. So you see, in Schwarzschild, if you wanted to do this perturbatively from Schwarzschild, you would just say, oh, this is box plus equals 0 and 0. So if you want to perturb, this is still done only for a very small. So it means that you're perturbing actually Schwarzschild into Kerr. But still, to perturb into Kerr, you need to know what the equation in Kerr looks like. So the problem in Kerr-Newman is that you don't even know how the equation looks like. You don't know what is this. You don't know what you have. So it has to generalize both this and the Reissner-Nordstrom that I showed you, because Kerr-Newman it reduces to both. So it has to generalize both. So first of all, it has to be a system. Second of all, it's gonna have these lower terms, fine. But you don't know how it looks like. So you cannot, if you want to do you're for sure you're gonna do first A small and Q small. That's for sure. But even to do that, you need to know what the equations are. Because for example, if you have additional terms like this, it could be a disaster. If you have something like a DDR, then it's done. You can't do it because it would be like a Totosky equation. It would be something that is not Lagrangian. So it depends on what terms will appear here with a Q in front, or something that would come up. So, and it's not, Chandrasekhar couldn't do it, but yeah, maybe with understanding that we have now. The problem with, you see, this is again just something that I hope at least it's what mathematics can give to the physics, is that at that time people were really only decomposing in modes. So that's the only thing you did, right? Your Chandrasekhar book is all decomposing in modes. And so if you look at what Chandrasekhar wrote in those pages, the issue that he finds is that you see the principal obstacle is in finding separated equations. So separated means in modes. So we should really consider the origin of this apparent indissolubility of coupling between a spin 1 and spin 2. So because in Kerr-Newman, like in Kerr, you don't have a spherically symmetric background, right? But you have an axially symmetric. So basically, if you have a spin 1 and spin 2, there's no reason an operator like a sort of Laplace operator on a 1 tensor and a Laplace operator on 2 tensor would commute. So in Kerr, it's surprising that it works. But in Kerr-Newman, what he tried to do is that it doesn't. So in this period, it does not work. So and the reason I think it may be because you started by decomposing in modes first. So there is hope, and I hope that one can actually do the way now mathematicians understand this without decomposing in modes. Just think about this one form and two tensors, and analyze them from as tensors, not by decomposing in modes. That I think that I don't see any reason why it wouldn't work, but I don't know how to do it yet. But yeah, I think that's a good. At least it's a good way of selling why we should do mathematical general relativity. It can give like some insights even on the physics that was not set till 30 years ago.
Okay, let's thank Elena once more.